In the name of the God, the most gracious, the most merciful. Assalamu alaikum, peace and blessings upon you all. The students, we today deal with the scheduling, the process scheduling, or we may say the CPU scheduling as well to this. In the beginning, when there was an open shop or a closed shop, systems, we have a user and he was given a system upfront, so we don't need any kind of scheduling. Okay, even though after that there was a batch processing of OSs when came up. Even in the batch OSs, we have a jobs being executed, sequentially, first come first serve basis. So there was typically no need of scheduling as well. But when we had a multi-programming environment, and all the time we try to execute multiple programs, and at that moment things become a little complicated, and we need some scheduler, the operating system's module, which is a scheduler which actually schedules all those jobs to the CPU. So how we do that is on the basis of certain criteria that we want to schedule, and we have a lot of algorithms for that, which has different efficiencies, and we talk about all those things. Okay, so typically scheduling is a mechanism to migrate processes to various states. Okay, actually these states may have maybe actually the queues. As you could see here, we have some process running, and there are many processes which are in a ready state. Okay, so which process, for example, you take from the ready state to schedule to the running for running. Okay, now there need to be some kind of policy which process we take. Should we take the process which is first, which have come first? It seems to be something good, but it's not, because sometimes we may see that it will be a big process. Okay, it hogs all the resources. Okay, and some short processes or short jobs may be on a back, which may queue up, which we call as a convoy effect also, which we will talk those things later. So that means there can be, out of the ready processes, we may choose some process on the basis of some policy, and which satisfies our particular criteria. Okay, we'll talk about that. So these things are done by the scheduler. Okay, and now we should also know that some processes are I/O based processes, or some are input-output based processes. Overall, there is a process will do some processing, okay, on a CPU, and it may have some I/O. It's waiting for something. Okay, maybe it's trying to write something on a disk. Maybe it's trying to write on a printer. Maybe it's trying to read something from the keyboard or whatever it is. There may be some I/Os. So a process will have some CPU burst and I/O burst. Okay, and in the meantime, when there is an I/O burst, we don't want our processor to stay idle, so we will be trying some other process. Now, which process you will actually load for the processor is actually the consideration of scheduler. Now, these are the criteria on which we actually schedule. Firstly, we want the CPU utilization to be 100%. Okay, we want to keep CPU as busy as possible. Now, there is a throughput the throughput says that how many processes you are executing per unit of time. So actually number of processes completed per unit of time. So more processes you are completing in a point of time, that means you're increasing your throughputs. Okay, so if you schedule processes in a better way, that means throughput is going to increase. Now there is a turnaround time. Turnaround time is something, for example, you go to the dentist. As an example, you go to the dentist, you arrive at the dentist clinic at this moment. Okay, say for example at time 1. But dentist doctor is busy with some other patients. What are you going to do? You're going to wait. So you're waiting, okay? And at this moment, say for example, the dentist came in and say it's your turn. You go to the dentist, and the dentist starts working on you. Say at this portion of time, you started working with the dentist, or dentist started working on your teeth here. So this piece of code time. Then maybe he has put something on your teeth, and you need some time for further processing. So in the meantime, the dentist go to the other patient. So you're again waiting here, right? And say 1 to 3 units of time, you started working. 3 to 5, 2 units of time of processing, and 5 to 9, you're again waiting, and then you are done. Say 9 to 11, you are again done. So in fact, your the work which has been done on you was 3 to 5, that is 2 units of time, and 9 to 11, again 2 units of time, that's 4 units of time. But how much time you have taken total when you came, okay, and when you are finished, okay? So then, so this amount of time, 11 minus 1, that is total 10 units of time you have spent to the dentist. Out of that, 4 units of time was your processing time, and 6 units of time was in fact your your waiting time. So this 11, which says actually the turnaround time. This is the total time you took from when you came and when you are finished. So that's what's called the turnaround time. Okay, and that means it has the processing time plus the waiting time. So what is the waiting time then? So some of the periods spent waiting in the ready queue. Okay, or in other words, it is waiting time will be the turnaround time, the total time minus the processing time. The time you are processed, you minus that with the total time, so that will come out the waiting time. That much time you have waited. Is it? And the response time is like this here. If we go here, you came here at a unit. It should be unit 0. Okay, so that will be make our 11 as a turnaround time. Otherwise, 11 minus 1 will be 10 as a turnaround time. Anyways, that technicality we'll discuss later on. Now here you came up here, and until 3 you didn't get any response. So at 3 you got the response, at 5, at 9 you got another response. But this time, up from 0 to 3, the first response you got is the response time. Okay, that is the response time. So these are the criteria which actually we take these things into consideration, that our CPU utilization should be more, the throughput should be more, turnaround time should be lesser, waiting time should be lesser, okay, and response time should be as quick as possible. So we have to choose a scheduling algorithm in such a manner which will satisfy these criteria. So the optimization criteria, we call it, is to maximize the CPU utilization, maximize throughput, okay, minimize the turnaround time, minimize the waiting time, and minimize the response time, right? These things should be minimized, these guys should be maximized. Now let us see the taxonomy of our scheduler, okay? Our scheduler, broadly speaking, can be either of 2 types on the basis of whether it is preemptive or non-preemptive, okay? Preemptive or non-preemptive. Okay, what does that mean? Now in a preemptive scheduling, you can snatch the processor from a running process, okay, even though it's not requesting that. If the process is not requesting, you can still snatch a process. Even if it's going on, you can snatch it, okay. Like we have a round robin, we'll talk about these things later on, these algorithms. Priority based schedulings or event driven scheduling, you can shortest waiting time next, SRTN, they are preemptive. And then non-preemptive, once you have given some, according to some policies, you have taken up some process, unless it doesn't finish, you're not going to take the CPU from it. Like we've got a first come first serve or shortest job first, okay. Even though you have made a shortest job first, that means you are not giving the processes on the arrival time, rather you are giving executing processes on the basis of shortest job, shortest burst length, okay. So but once you have given some process, chosen some process, now you will not snatch CPU from it. That is the non-preemptive scheduling. That's guaranteed when it goes to CPU, it is done until it doesn't finish, okay. Basically, when you are scheduling, this scheduling actually does lot of things. Okay, it not only maximizes your throughput, which we talk about. Okay, it makes processing a bit predictable. Okay, a given job, what I mean actually is a given job should utilize the same amount of time and should cost same regardless of the load of the system. It will also try to minimize the overhead. Okay, if we have an overhead, we're going to try to minimize it. Okay, uh, it should balance the resource usage. So we have resources, and we should balance it among the processes. We should avoid indefinite postponement. Okay, it should not be like you're postponing some processes and they are starving. You should be able to raise their priority and so that they get the CPU. Okay, that's what we call it. We can enforce the priority. Priority can be fixed, or you can actually increase priority of certain process which is not getting the processor quite often. Okay, and you give preferences to processes if they are holding certain key resources, so that those resources will get free and you can distribute that and balance those resources among other processes. And if there is that you are degraded, okay, means there is some problem. If you want to degrade, you degrade but gracefully. This is what this scheduling is all about. And our scheduler is of three types. Okay, one is the long-term scheduler, second is the medium-term scheduler, and the third one is the short-term scheduler. Let's try to discuss these things. Now, long-term scheduler actually selects a job or a process from the process pool. Okay, like we have a batch system, often more jobs are submitted that can be done at once. Okay, so some are spooled out to the mass storage device, and the long-term schedule actually selects from them the which processes it loads the processes from the spool area of the hard disk into the memory. So it actually controls the degree of multi-programming. So when you see in the diagram the new process here, it is actually done by the long-term scheduler, which gets processes from the process pool and introduces them into the here for the operating system to schedule. So because when you get the process into the memory, that doesn't mean it's gonna running. Okay, we have to do a few more things before it gets running. So typically you select some process from the process pool and you actually are increasing the degree of multi-programming. That means the more process you get into the RAM, they are all gonna schedule for processing, right? Now short-term scheduler, when the processes are in the memory, okay, here they are in a ready state, they got to be scheduled for running. So this thing will be done by the short-term scheduler, and this is going to be more frequent, and this is going to be less frequent, the long-term scheduler, which comes, sometimes it gets in. But here, when the processes are in a ready state and they got to be get running, so this is the short-term scheduler which does this. And there's sometimes, you have too many, for example, you're seeing the throughput is not kicking up, and there is some problem because maybe we have a lot of programs here in a ready queue in a memory, and we are not balancing the resources, taking a lot of time. And so what we do is we try to reduce the multi-programming, so degree of multi-programming. How we do that? We, out of these processes, maybe we choose some processes and swap them out, okay, into some area of the hard drive or virtual memory or somewhere else, so that the degree of multi-program is reduced, and at later time, we get them back, okay. So this thing to reduce the degree of multi-programming by swapping certain processes from the memory back to the hard drive or virtual memory or wherever is done by the medium-term scheduler, okay. Now here, the long-term scheduler or short-term scheduler, sorry, the medium-term scheduler is actually not of a concern, because the main concern of the policy which we're talking about is that when we have in a ready queue some processes in RAM, out of them which processes should be scheduled for running. So this is where we have our policy and scheduling algorithm. Okay, and we have many of them. Let's see. So this is scheduling algorithms, and about actually the short-term schedule we are talking about here. The first one, which is quite straightforward, is FCFS, very simplest. Okay, but it has its problems. We discussed them, and then we move on to the shortest job first, then priorities, round robins, multi-level queues, and multi-level feedback queues, and all of those. And there are many more. So we will see all of them one by one, and let us first take up the first come, first served. The first come, first served scheduling is kind of very simple. The process that requests the CPU first, say for in this process requests the CPU first, it will be given CPU, and the next one the next, and the next one the next, and so on. Okay, it is non-preemptive, means you are giving process 1 to the CPU until it doesn't finish. You're not going to relinquish the CPU. Okay, when it is done, you go to the second, and that is done, you go to the third, and so on. The average waiting time for the FCFS is going to be long, and because it has a convoy effect, and we see all those things now. So this is our example, and I add arrival time to this. Say this has come at time 0, this came up to 1, and this came at time 3, or something like that. Okay, these are processes P1, P2, P3, for example, and then got a burst time in milliseconds. The 24 burst time it needs, the processing time it needs is 24, then this P2 needs 3, and P3 needs 3. And the first thing is to make the Gantt chart. So we will make our Gantt chart, okay, for the schedule of this schedule. So starting from the time 0, we start the P1 first, because this has come the first. You have to give it to the CPU first. And it finishes at 24 units of time. So it finishes at 24 units of time. Then after that, we can load the P2. No problem. We can load the P2, which has a 3 units of time. 24 plus 3 is 27. And you got a P3. You can load the P3. P3 is arrived at, say, 3 units of time. Okay. So it finishes at 30. Now we'll make a table out of it, so that we'll see average waiting time and average turnaround time. Okay. So firstly, we have got the processes. These are our processes: P1, P2, and P3. Arrival time at 0, 1, and 3. Then we've got a burst time, that is 24, 3, and 3. Okay, it's going on. Now we got the turnaround time, and we got the waiting time. Okay, here. Okay. So what is the turnaround time of the P1? Turnaround time is the total time minus the arrival time. Okay, a total time of finish is 24, or finish time is 24 minus 0, that's going to be 24. And what about for this? This is finish time is 27, arrival is 1, so that's going to be 26. And what about this? It finished at 30 and came at 27. Sorry, it came at 3. So this is going to be something like what? 27. So 24, okay, 26, and 27. Now what about the waiting time? Waiting time is total time minus burst time. So 24 is the total time, burst time is 24, is going to be 0. What about this? 26 minus 3, that is going to be 23. 27 minus 3, that is going to be 24. Or what about now average average turnaround time is going to be, you have to add the 24 plus 26 plus 27 divided by 3, okay? And same you do with the average waiting time. That is going to be 0 plus 23 plus 24 and divided by 3. So this is equal to something like 25.67. Okay, and what about this now? And this is something somewhere like 15.67. Okay, so this is the average waiting time, this is the average total turnaround time. Now let's take another example. We have the you should in this example see what is the arrival time. Okay, that's important. Sometimes people forget to see what is the arrival time, so then calculate wrongly. Now this is the burst. We have processes A, B, C, D, E. This is the arrival time of them. Note E is come at time 12, and burst length is 35255. So this will be the Gantt chart. Simple 3 first, and then B will have a 5 units of time. 3 plus 5 is 8. C will need 2. 5 plus 8 plus 2 is 10. 10 plus 5 for the D is 15. 15 plus 5 is 20 for the E. Okay. Now if you look at the E has came at 12 and finished it at 20. So the TT will be 12, right? So don't get confused if it is 20 here. Now pause the video and calculate like above the average turnaround time and average waiting time. Okay. Now this is another example. Now we have the arrival time, the processing time, or sometimes called the burst time. We even call some process also the bursts, whatever you like to call them. Now 33142, and this is our Gantt chart, and we have calculated our turnaround times and waiting times. You just now calculate the average turnaround time and the average waiting time. Okay, do it. Pause the video and do it. Now you must have done it. Just check it. The turnaround time is going to be all the turnaround times divided by 5, that's 6.2, and average waiting time, or add all the waiting times plus divided by 5. And process utilization is simply 13 over 1300, that is 100%, and throughput, because we completed 5 processes in 30 units of time. That's what I said the throughput is, number of processes completed over unit time. That is 0.3838. Okay. Now there is a problem with the FCFS. It's simple, but it's not that good. Okay, because say for example we got what's called the Convoy Effect with this FCFS. What does that mean? Maybe we have, say for example, a bike. We have a bike rider, for example. If you consider this a bike, if you doubt, I don't know what is this. So this is a bike. Okay. Anyways, now you can go through this road. You have to go this way and go to this way. Okay. Now, but from this way, a convoy is coming, and you are stuck after it. Unless the convoy doesn't pass, you can't go through. Okay. Now you could have, this bike could have gone in a fraction of a second. Okay, on this side, if you would have given this bike a chance. And maybe you stop at the convoy and say, hey, let the bike go first. That's what we call the shortest job first. That if you have a short job, then let it go first. But if you do first come first serve, the convoy has come first, the shortest job, the bike has to wait for long. Okay, say for example here, first job which came is the 100 units of time. The second one which was there is just a 1 unit of time. Now this one has to wait for the 100 units of time to finish. So average waiting time and average turnaround time is getting increased. Okay, so it would have been better that you first, finish the one, because 100 has to wait for 100. If it goes on in 100:01, it doesn't affect that much for a long job. Say for this convoy, if this bike took 1 minute to pass, and this convoy will take 1 hour to pass. And this convoy will not have that much effect if it finishes in 1 hour and 1 minute. Okay, but this bike will have a huge impact of this waiting. Okay, it's waiting. It could have done it in a 1 minute. Now it is doing it in a 1 hour and a 1 minute. So it is taking a long time for getting the response. Okay, and what we promised is that we will balance the responses. We balance the response time. We balance the resources. And we'll try to increase our throughput. So that's where our FCFS failed. Okay, but if you have got a long jobs, okay, then FCFS is going to be the only way because it's the simplest without any lot of overheads and all. Okay, so we try to see all these problems again and try to mitigate these problems in our next video where we take up the SJF. Okay, so see you there in the SJF video. Until then, God bless and